In this video, we're going to discuss the constants of equilibrium. So previously we had a reaction that said N2O4 is in equilibrium with 2NO2. We assume that these steps of these reactions are elementary, so that my K forward times my concentration of my starting material would be equal to my rate forward. And that my K reverse times the concentration of NO2 to the second power would be equal to the rate reverse. At equilibrium, these must be equal to each other. My K forward times N2O4 must be equal to K reverse times N2O2 squared. And these would be the equilibrium concentrations. This is the only time the rates would be equal to each other, so these expressions would be equal, would be when you are at equilibrium. So the only concentration where this is true is the equilibrium concentrations. Well, we can reorganize this a little bit. Let's get the concentrations on one side and the K values on the other. So K forward divided by K reverse must equal the NO2 squared over the N2O4. What we find is that at equilibrium, the ratio of our products and our reactants is equal to a constant, which is the ratio of our K values forward and reverse. This leads to a new constant, the K of our concentrations, the K of equilibrium, various ways to write it, an equilibrium constant. The equilibrium constant is equal to the products over the reactants. Since this gives us a value based on the concentrations at equilibrium, depending on what our equilibrium constant is, gives us an idea how much our reaction proceeds towards products or not. If our K is much, much greater than 1, well, think of any division. I must have a lot on top compared to the bottom, so that when I divide, I get a larger than 1 value. If that's the case, then I must be largely products. This means that this reaction proceeds almost to completion. It very much dominates by products. If your equilibrium constant is much, much less than 1, well, how do you get a number less than 1 from division? You must have far more on bottom and far less on top, so that when you divide, you get a decimal value much less than 1. If this is the case, then our material is largely reactants. This means the reaction has barely proceeded. And if our K value is somewhat near 1, 100 down to 0.01 type area, then we have relatively close amounts. Definitely noticeable lack of all the material converting, definitely have to clean out unused starting material that would be a contaminant in your product. If our K value is somewhat nearish 1, then we have to deal with the fact that we definitely did not use up all of our starting material. K's of equilibrium are constant at a temperature for a given reaction. So if you were to start with some N2O4 and none of your products, it would convert over time, you'd build up a little reverse, and eventually you'd reach your equilibrium concentrations, whatever those were. We'll plug that into our equation up above. That K value must be equal to the NO2 squared over the N2O4. Once you reach equilibrium, the concentrations that you would have when you plug in will give you some K value. That's going to be true regardless of how much starting material you started with. Do this again, but start with 800 of the starting material. It's going to react more. It's going to take some time to do it, but eventually it's going to reach some equilibrium concentrations as the reverse builds up. Whatever those concentrations are, well, they will both be larger than when we only had 100 molecules to start breaking down. When we plug them in, they will still give the same K value. Because it is just a ratio of our products to our reactants, you can have them scaled larger or smaller, and when you do the division, you'll still get the same K. Equilibrium constant is always the same for the same reaction at a set temp. It does alter with temperature, but for reactions done at standard temperature, where most of our K values are located, we will find that that K value is always what is the equilibrium constant. No matter how much starting material we started with, or even if we started with product. You very much could have started this with 0 starting material and 300 some product. We'll just do the reverse reaction for a while. Eventually it starts building up the forward reaction until the two are equal. Whatever concentrations you then have, when you plug them in, will be equal to the same equilibrium constant. Because the concentrations will alter until their rates are equal. For a given amount of material, there's only one possible mix of concentrations where that will be equal, and that ratio of those concentrations will always be the same constant. This is wonderfully convenient. It means it does not matter how much of the starting material, or even if we start with a mix of starting material and product, they will always adjust to equal the same ratio. Well, how do you know if you're there yet? When you throw in various amounts, you may or may not be anywhere near equilibrium yet. For this, we need the Q value, the quotient. The Q value is the ratio right now. Instead of the K value, which is the ratio of products over reactants at equilibrium, the Q value is the present mixture. Have we reached equilibrium yet, or is it still early and they're still adjusting? If I have A in equilibrium with B, and I have 100A and 0B, we'll say that our K value is equal to 0.5. Well, if we think about our reaction here, my K is going to be equal to concentration of B over the concentration of A. To have 0.5, I must have more on bottom than on top. I'm less than 1. So I'm favored towards reactants. If I plug these values in at the moment, well, you can't divide 0 by something successfully, really. So initially, not very good. But over a little bit of time, A decreases and I get some B. And maybe over a little bit of time, it happens again. And eventually, we'll get even further down. Let's say we get to this point. 10 of my starting material have converted. Well, I go and plug that in. I say, hey, my B is presently 10, my A is 90. So if we take 10 divided by 90, we calculate 0.111 repeating. Well, that is much smaller than K. If we think about our division, that means I have too little on top. I need top to be bigger so that my value calculates out bigger. Or I need my bottom to be smaller so my value calculates out bigger. Or in reality, I need both to happen since I'm transferring my bottom to my top here. What this means is that this reaction hasn't finished. My rate forward still exceeds my rate reverse. I haven't reached equilibrium yet. This value, this is our Q value. Your present ratio of your products to your reactants. Q changes for every different possible mixture. K is always what you'll have at equilibrium. So to compare Q to K lets us know if this reaction has finished or if it's still going and in what direction. Is it going to create more products and use up more starting materials? Or is it going to do the reverse, make more starting materials and use up more products? If our Q is greater than KEQ, well, think about a ratio. You've got products on top, and you've got reactants on bottom. If our calculation is too great, I must have too much on top, too little on bottom. So if your mixture at the moment gives you a value greater than your equilibrium value, then you have too much product. The reaction moves towards reactants. On the other hand, if your Q is less than KEQ, as we saw in our example here, well, the way for that to happen is the value on bottom must be too large. It's making my division come out much too small. So I need less on bottom. If you put a larger number on top, that will also increase the value you get. So if our Q is presently smaller than the equilibrium constant, I must need to put more on top of our division, less on the bottom. I must need more products, less reactants. In this case, the reaction will continue and it will move towards products. Sometimes this is also referred to as moving to the left or moving to the right, as our products are always written on the right and our reactants are always written on the left. If our Q is ever equal to our KEQ, then we must be at equilibrium. So the K value gives us the ratio of our products to reactants at which we will be at equilibrium, where our rate forward will equal our rate reverse. Q tells us our present ratio, and comparing that to KEQ lets us know how the reaction is going to continue for a while. Is it going to use up reactants and make more products? Is it going to use up products and make more reactants? Or has it finally reached equilibrium? So referencing our present mixture versus the constant lets us know what is occurring with the reaction as time will continue.